Hey, ladies and gentlemen, today we are going to be doing the dissection of a brain. That's right, a real brain. Now, unfortunately, it's going to be a sheep brain, not a human brain. I tried to get human brains. Please got involved. It was a big thing. Don't ask questions. All right, so we are going to be using sheep brains today. But before we go into that, let's actually look at a human brain. Not a real one, but a model. And this is what a human brain looks like. Not that hard. It's actually very, very soft in real life, almost like silly putty, even softer than that, slightly stiffer than pudding. And it consists of a bunch of lobes that we've talked about in class. Coming closer, we have the frontal lobe, and up here, the parietal lobe. In the back is the occipital lobe. You can see the separation right there. And then on the side, we have the temporal lobe. And we talked all about in class about what those lobes do. Today we are just looking at what they look like now. On the back, shown in green, but it's actually the same color as the rest of it in real life, is your cerebellum. All the lobes make up the cerebrum. Back here is the cerebellum, and look at that, it's kind of hanging free, it's loose, it's actually its own separate section. The cerebrum and cerebellum are not actually attached. The cerebellum is attached directly to the brainstem. So that is the inner workings of the brain, or the outer workings of the brain. The inner workings, if we can take it apart, the inner workings are also what we talked about in class. We have the corpus callosum, the thalamus and hypothalamus, brainstem, pons, and the medulla oblongata. Had to stop and think about that word for a second, almost forgot it. And you can see that cerebellum is not attached to the cerebrum. The little brain in the back, we call the lizard brain, I like to call the zombie brain, is not directly attached to the higher order thinking cerebrum. Right? It's its own little brain on the brainstem. So now that we got this for comparison, let's take a look at the brain that we are going to be dissecting, the sheep brain. The first thing you're going to notice is size. Look, this thing is tiny compared to that human brain, right? You know, sheep actually aren't as smart as humans. You know, this is the reason why. Size of the brain compared to the size of the body. You know, our brains are bigger for our body than theirs to their body. So not as much brain work. They're not as intelligent as us. But another thing you're going to notice about this is the shape. Look at that. This is going like almost like an oval, almost like it looks like a balloon, right? A deflated balloon. Where ours, not quite that shape. Yeah. The reason for that is the brainstem. Our brainstem is going downward. Why does it do that? Because we are designed to be standing up straight. Our brainstem continues down the neck as we stand up straight. Where the sheep doesn't stand up on two legs, it stands on four legs. So its spine is actually going to be going outward along its back. Its cerebellum, instead of being down here, is going to be pushed up here in the back instead of below. The brainstem goes out back too. Another thing you're going to notice is it has a covering on it. It looks like it is saran wrapped, like whatever company sent this to us has it packaged. No, we already have it packaged up here in our heads. This is an epithelial covering. Every organ in your body has a covering. Remember, we talked about that? This is your brain's covering. It is called the meninges. It's actually 3 layers of covering because your brain's that important. It needs 3 layers. Those 3 layers are called the dura mater, the arachnoid matter, and the pia mater. What you're looking at is the dura mater, the thick stuff on the surface. And yes, I am going to remove this when we actually get into the dissecting part of it, but not yet because I want you to see underneath. And so guys, in order for your brain to be aware of what's going on, it needs nerves to go into the brain. Once I cut this covering off, I'm probably going to cut some nerves off too. I want you to see those nerves. Look in close. Look, look, look. This is underneath. Right? This is the brain. The sheep is looking for, like, going in this direction. So underneath, we got some nerves sticking out. These 2 nerves are called the optic nerves. Eyesight. So as the sheep stands like this, these nerves, if I can actually position it, these nerves are sticking out and go attached to the eyeballs. So the sheep's eyes would be right about here. Then look closer. It looks like right here, it looks like weird blunted teeth almost in my camera. No, those are even bigger nerves. Those are called the olfactory nerves, right? Up here, for the nose, for a sense of smell. That's what olfactory means. It means smell. So the sheep have much thicker, larger olfactory nerves than they do the optic nerve. So what does that suggest about sheep, about their senses? What would be stronger, a sheep's sense of smell or the sheep's sense of sight? No, right. It would be the sheep's sense of smell because they have much thicker nerves going in. They get a lot more information from their sense of smell than they do their sense of sight. Okay. Now, to look further than this, we're going to have to cut this dura mater off. So let's get cut. I am not actually going to start off with my scalpel. I'm going to start off with my scissors because I want to cut this dura mater off just like any other covering. It's easier to do that. So I'm not done yet. I only managed to uncover the cerebrum because I wanted you to see the lobes first. But I also want to pick out another difference. You will notice with the human brain that there were a lot of bumps and grooves, what we call gyri and sulci. Gyri are the bumps, sulci are the grooves, the wrinkles. And you notice that there are a lot less wrinkles in this brain. It's actually pretty smooth to the touch. So remember, the reason why we have those wrinkles in our brain is because as your brain grows, you run out of room. It's inside of a skull. So in order for your brain to get bigger, it needs to cave in on itself. Take this paper ball, for instance. If I wanted to add mass to this paper, because it's a brain and it's getting smarter, right? But it can't get any bigger because it's trapped inside the skull, I'm going to have to bend it inward instead of outward. It's going to get denser and it's going to get much more wrinkled. And that's what happens to your brain. As your brain gets bigger, it's actually going to fold in on itself and get more wrinkled. And this sheep doesn't have many wrinkles. So what's that say about the sheep's intelligence? Does he think the sheep is smarter or less intelligent? Is it more intelligent or less intelligent because of that? Right, it's going to be less intelligent. If it was more intelligent, the brain would grow and have to fold in on itself, be wrinkly. Now let's take a look at the lobes. We got the frontal lobe up here, named accordingly, it's in the front. And in the back, we got the parietal lobes. What we cannot see very well, because I still have this in the way, we got the occipital lobes in the back. And then on the sides, you really can't see it very well from this angle, but if I hold it like this, that should do it. You see a bit of actually you see better on this side, a bit of a bump sticking out right there. That is the temporal lobe. And a temporal lobe is a good place to house a whole lot of memories. And the human temporal lobe is pretty substantial. It's pretty noticeable. The sheep's temporal lobe, not so noticeable. So again, what does that say about the sheep's memory capacity? Right, not that good. It's not going to have a good job remembering what's going on. Let's continue removing this dura mater. First off, you'll notice that I made a bit of a mistake because I'm trying to work at a weird angle so you can see. Normally I would be like this cutting, right? But I accidentally ripped a bit of the brainstem off. So, oops, but it's fine. You see right here where it's supposed to be. So it falls off later. We got an idea. But another thing I want you to see before I continue cutting is, and I've never been able to get this really well without ripping this before, so you guys are in luck. You see that string looking thing right there? That's the optic nerve, right? It's coming in through there and out there. So you can actually see it go toward the outside. So it's not as thick as it looks. It's so thick right here because of the dura mater covering. But in here, it's actually pretty thin. compared to the olfactory nerve, which is super, super thick right up in here. And here we have the entire exposed brain with a little bit of the dura mater still on the bottom so I can hold on to those optic nerves. Not that I need them anymore. And again, first thing I showed you before was the cerebrum and the cerebellum are not actually attached to each other. You can see some pia matter still trying to hold it in place. That's actually going to rip as I pull it. That goes like webbing, right? That's just the epithelial covering. I didn't actually rip any brain. All right, so you see that they're not actually attached to each other. The cerebellum is attached to the brainstem. So really, you got two brains working together, not even attached to each other. What we call the lizard brain, with a bunch of instincts and balance and things like that. And then the cerebellum is the higher order thinking. You have the thoughts and emotions. So let's make a cut. First thing I'm going to do is cut very gently. I'm not going very deep. Remember, you got two hemispheres. You have the left hemisphere and the right hemisphere. And again, they are two separate brains in and of themselves, really, but they're attached. They're attached by something called the corpus callosum, a bundle of nerves right in the middle. Right in this middle area, this crack called the longitudinal fissure, there is a bundle of nerves going back and forth. So I want to try to cut that, this pia mater. I have managed to do this next step maybe once, and not on camera, where I want to try to peel this back and so that you guys see if you can see the corpus callosum before I tear it. Nope, too much pia mater still in there. And yet again, I failed. I may have actually cut it with the scalpel that time. So I'm just going to go ahead and cut this in half all the way now, and we'll just take a look at the inside. And notice it looks like I'm having a pretty tough time with this. I told you the brain is super, super soft. That's because this brain has been preserved, and the preservative chemicals actually harden it up a bit. So it's actually the consistency of a really strong rubber right now. And here we have the brain cut in half, being held together by the bottom dura mater I didn't cut off. So let's cut through there. There we go. Now let's take a look at the inside. First off, take a look at the inside of the human brain. The colors. We see the corpus callosum, what I was trying to show you, that would have connected the two sides. And we can see that very clearly in the sheep brain. It's a nice white layer right there, corpus callosum. And then underneath that, we can actually see better on this side. When I get the matching human brain. Underneath that, we have the thalamus and hypothalamus. And that's what we're looking at here under the corpus callosum. We're taking a look at the thalamus and the hypothalamus. So as all the information comes in from the brainstem, it hits the thalamus, and the thalamus decides which part of the brain that information is going to go to. It organizes all the impulses coming in. And because I cut a bit of the brainstem in a haphazard kind of way, jagged kind of way, I wanted to show you the pons, which would be around here, but it's not really showing. Normally it shows pretty clearly. On camera anyway, I don't think it is, but there's a slight shade difference with my real eyes anyway, not my camera, but my eyes see a slight shade difference, and that would be the pons. And anything under here be the medulla oblongata and midbrain up in this region. So now we are going to do something called a lobotomy. Now remember, the eyes were right about here for the sheep. A lobotomy is when doctors used to, they don't do this, by the way, because it's very, very bad. They've learned that that doesn't help anybody, that they thought people were going crazy because something was wrong with the frontal lobes of their brain that they knew handled personality centers. So they would actually take a probe past the eye, into the eye socket, not actually damaging the eye, hopefully, but into the frontal lobe, and try to cut a piece of that frontal lobe off, hopefully removing the part that they thought was not working properly. So let's take a look at the inside of that. They've learned since then that lobotomies don't actually work and no one does them anymore. But if we were to cut that frontal lobe off, what would we really see? Is quite a color difference. It looks like we're looking at the like branches of a tree. Remember, your brain is made up of what we call gray matter and white matter. Now, this doesn't look very gray because of the preservative chemicals. It looks more like a tan now, but it is a natural brain, a bit grayer once you remove the blood. And then on the inside, it's a bit lighter. We call it the white matter. The gray matter is where all the synapses are, all the dendrites and the axon terminal, interacting with each other, sending information. So all of your thoughts are out here on the surface where all the gray matter is. And then the white is all the axons, the tail of the neuron, right? Once the information is shared in the synapse, an electric impulse can travel through these axons, going in all these different directions because there's all a bunch of different axons there, sending information to different parts of your brain. That's what the white matter does. You have a thought here in the front, and the white matter axons can send it over here into the back where your side, you have some memory and processing. Over here is the occipital lobe. If we cut that off, we're in the back of the brain now. You would see much of the same. So if occipital lobe handles sight, take a look here. If you remember, we got the optic nerve showing, right? As it comes in this way, I got hold my glove. As it comes in, this is the front, comes in here, it continues to the back, because look at the angle. Continues to the back, so the back of your brain is actually handling eyesight. And then this white matter is going to send that information to the front where you can process it and have emotions about what you're seeing. Take a look here. We are looking at, let's get to this whole brain so you have a better idea now, and the more whole. We got the cerebellum. The cerebrum is in the top, cerebellum's in the back. When we look at it, the cerebellum also has much of the same. Looks like white branches on the inside, but it's only communicating with itself and the brainstem. Those white branches do not reach out, this just connective tissue there, do not reach out to the cerebrum. So independent thought right here. Where here, we got some more white matter. That corpus callosum is a type of white matter that shared information with this side of the brain. All right, ladies and gents, that is the brain. If you ever want to come visit me when it's safe to come back to school, I will let you dissect the brain and give you that experience. All you got to do is come visit and ask. All right? All right. Ladies and gentlemen, have a good day.